Hello, welcome to ChemBio and to A-Level Chemistry revision. In this video, we'll look at electronegativity and polarity, two very important concepts in chemistry. Stay tuned. So as mentioned already, this topic is very important. There are so many exam questions that test your knowledge on this, so it's absolutely paramount that you pay attention. So let's get started right away, let's get straight into it. I'm going to show you the definition for this term, write out the specification, write out the textbook, which is the ability of an atom to attract a bonded pair of electrons in a covalent bond. This is what we refer to as the atom's electronegativity. So in this series of videos at the moment, we're only talking about molecules. So we're only interested in covalent bonds, okay? So therefore, to explain this, I'm going to use a covalent molecule. And you know that I like to use ammonia as an example, so that's what we're going to do. Here is the dot and cross diagram for ammonia. So you can see that we have one covalent bond here, and one here. From the definition, we're only interested in one covalent bond, so we'll only focus on this one for now. Also, we're only talking about the bonded pair of electrons, so we don't need to worry about the other ones for now. So, both of these atoms here, nitrogen and hydrogen, have an ability to attract this bonded pair of electrons right here. One of these atoms, though, will have a higher ability, and that one will be nitrogen. It happens to be that nitrogen attracts these electrons more than hydrogen. That means that these electrons will move closer towards nitrogen, quite simply because nitrogen attracts these electrons more than hydrogen. We can say therefore that nitrogen has a higher electronegativity than hydrogen, or nitrogen is more electronegative and hydrogen is less electronegative. Now, because this bonded pair of electrons has moved closer towards nitrogen, we will have a more negative charge on the nitrogen end of this bond. The hydrogen end has sort of been freed from negative charge. The electrons have moved away from hydrogen. We will therefore have a slight positive charge. Now please pay attention to the word slight. This is not a full charge. Hydrogen is not giving away any electrons. Nitrogen is not accepting any electrons. Remember that in a covalent bond, the electrons are shared. They're still shared. Nothing has changed. It's just that this shared pair of electrons is moving closer towards nitrogen. And as a result of this, we get an accumulation of this negative charge on the nitrogen side, on this left-hand side of the bond, and therefore we have a positive charge on this end, and only slight. To show this very slight positive or negative charge, we use the Greek letter delta. Nitrogen end will be delta negative, hydrogen end will be delta positive. And this symbol delta means that the charge is only very marginally positive or negative. It's less than 1. Now with ionic bonding, we're talking about full absolute charges, which are whole numbers, such as 1 plus, 2 plus, 1 minus, 2 minus, and so on. But that's all ionic bonding. That's when we're forming ions. So electrons are being lost. They're being transferred from one atom to another. This is not the case in electronegativity. No. Forget about ionic bonding. We're not interested in that at the moment. This is covalent bonding, where the bonded pair of electrons is just moving in between these two bonded atoms. No transferal of electrons is taking place. It's just this pair is being displaced closer towards nitrogen. That's it. Now pay attention to the word atom. We're talking about the atom having an electronegativity. Now of course every atom is assigned to its element, of course, and we can also talking about elements having their electronegativity. But just remember that elements themselves, they can't attract electrons. It's only the atoms, okay? So when giving the definition in an exam situation, always write atom and only atom. Now you're probably wondering, why is it that nitrogen can attract these bonded electrons more than hydrogen? Now, each atom, as you can see from the definition, has its own ability. Every atom of every element that we know will have its very own ability to attract a bonded pair of electrons. And luckily, we've managed to spot patterns in these abilities of atoms across the periodic table. So we can therefore deduce some electronegativity trends. And you'll be very happy to find out that these electronegativity trends are exactly the same as for ionization energy. Remember that ionization energy is to do with removing a valence electron from an atom, while with electronegativity we're also talking about we're also talking about outermost electrons, because remember, in a covalent bond it is the outermost electrons that are involved in the bond formation. So, just as a reminder then, factor number 1 is atomic radius. We know that it decreases across a period. This means that the valence electrons are more strongly attracted to the nucleus. Yes, so the electrons are, in terms of distance, they are closer towards the nucleus, therefore the attraction is going to be greater. Common sense, really. This means that electronegativity overall increases across a period. Question is though, why does atomic radius decrease across a period? Well, that's to do with the next factor, which is nuclear charge. Nuclear charge increases across a period due to the increase in atomic number, yes? This means that the outermost electrons experience a stronger force of attraction with the nucleus. Why is that? Well, we all know that the principle of filling up electron shells, the filling up of all the orbits, is such that we start off with the first energy level having 2 electrons, yes? The formula, by the way, is 2n squared. First energy level will have 2 electrons. That stays the same across the whole period. Nothing changes. We're only adding electrons to the outermost shell. The innermost shell is not affected. Nothing's happening to that. It's all the same. Therefore, the innermost electrons, the ones on the first energy level, they experience more and more attraction as the number of protons increases. And the number of protons increases across the period because we have an increasing atomic number, quite simply. So there is more and more positive charge in the middle, and then those 2 electrons, the number of electrons isn't changing, they're being pushed more and more towards the nucleus, and therefore the distance between the nucleus and the electrons is decreasing, and all the other electrons consequently are also pulled closer towards the nucleus. Anyway, that's a bit of a side note. We don't really need to know about that. We just need to know that overall nuclear charge increases across a period. Therefore, electronegativity also increases across the period. So as you've guessed, the principle is very similar to ionization energy. Just remember that our conclusion is not ionization energy increases across a period, but electronegativity increases across a period. The last factor, as you know already, is of course shielding. And the effect of shielding is very similar across a period, so we tend to ignore that. However, shielding increases down a group, quite simply because we're increasing the number of these energy levels. More shells, more shielding from inner electrons, so it's harder to A, remove the outermost electron, that's to do with ionization energy, and B, to attract that electron to the nucleus. So therefore, in combination with also the increasing atomic radius, remember that the atomic radius will also increase for the same reason of there being more energy levels, overall we can therefore conclude that electronegativity decreases down a group. Therefore, summarizing the trend of electronegativity, it increases up a period and across the group. There we go. Here's just a graph to show you how atomic radius changes with atomic number, and you can see here all of these areas here are the periods. Every time we increase our atomic number, our atomic radius decreases each time. As soon as we start a new period, we're adding on an extra energy level, and you can see this massive increase in atomic radius. Just shows how important this fact of atomic radius actually is. Right. Now, ionization energy has proper units. With electronegativity, they're only arbitrary or relative. Instead, we actually use a scale. We have a scale of electronegativity. It has been determined. It was devised by the famous scientist Linnaeus Pauling, and it varies from 0 to 4. 4 being the highest electronegativity, 0 therefore being the lowest. Which element will therefore have this value of 4? Which one will be the most electronegative? Yes, exactly, it will be fluorine. Because if we look at the periodic table here, we can see, we've already said that the trend of electronegativity is such that it increases up a group and across a period. Now, ignoring the noble gases, fluorine will therefore be in the top right-hand corner of the periodic table. That's why it has the highest electronegativity. Francium, therefore, which is in the bottom left-hand corner, will have the lowest electronegativity of 0.7. Now, as you can see on the periodic table, we have all the values of electronegativity. However, for A level, we of course don't need to know them. We only need to be familiar with the trends. So if I remove the periodic table now, can you tell me which atom out of magnesium and boron will have the higher electronegativity? Yes, of course, it's boron. It's higher in the periodic table and it's further right. That means its electronegativity will be high. We don't need to know any values. We just need to know the trends. That's it. And here's another graph just to illustrate this a bit better. As you can see, there we go. At the very top, we have fluorine with 4, and at the bottom here, we have francium with 0.7. Now, it's all well and good knowing about this idea of electronegativity and electrons being displaced towards one atom because it has a higher ability of attracting those electrons. Where can this actually be used? Well, this is where we bring in polarity. We can use electronegativity to determine the type of bonding between two atoms. We use the difference in electronegativity between these atoms. So we take the atom with the lowest electronegativity out of the two and we subtract that value from the other ones, and we're going to get the difference. And now if that value is 0 or approximately 0, then the bonding between these two atoms will be covalent, pure covalent. Okay, now when we say approximately equal to 0, if it's slightly above, then we still count it as covalent. So if the difference is greater than 1.8, it's an ionic bond. Now, to be honest, we don't even need to use electronegativity to determine whether the bond is ionic or not. We just know that metal plus non-metal, well, that's an ionic bond, usually anyway. And this is where the important part of this video comes in, a difference between around 0 and 1.8, so between these two values, that is a polar covalent bond. A polar covalent bond. Now you can see I've given you values here of 0, 1.8 and so on. As mentioned already, we don't need to know these values, we just need to know the trends. And basically, if the difference is very small, covalent. If the difference is very large, ionic. If the difference is, well, between the two, then it's a polar covalent bond. That's all that you need to know. Now, when we say approximately equal to 0, there are a few exceptions whereby the difference in electronegativity is slightly above. For example, CH has a difference of 0.4. We still treat that as a non-polar bond. So all organic molecules that have CH, they are still all non-polar, okay? That's just the fact, that's just what we accept it to be. That's just what the scientific community has agreed upon. CH is a small enough electronegativity for it to be non-polar. What is this polar covalent bond then? Well, it's still covalent, so we're still talking about sharing of electrons, but this is where our idea of electronegativity comes in. When we have a difference in electronegativity that's not large enough for it to be ionic, of course, but just ignore ionic for now, this difference causes an uneven distribution of electrons. We saw this at the very start of the video. Those electrons between nitrogen and hydrogen, remember, they moved closer towards nitrogen. They're more attracted to nitrogen. That is what we mean by uneven distribution. Alternatively, you can think of this with the electron cloud. Now, if this confuses you, don't listen to this. Otherwise, remember that we kind of disregard this whole idea of the model of the atom where we have the nucleus and these circles around them which depict the energy levels. The correct or the more correct representation is thinking of the electron cloud, where electrons just basically move around the whole nucleus in this very large spherical or oblate spherical shape. When the bonded pair of electrons moves closer towards one side, then we have a distortion in this shape of the electron cloud. It becomes slightly skewed. One side of this electron cloud will be larger than the other because the electrons are more likely to be found on the end, which is more electronegative. You'll see what I mean in just a second. I'm going to show a diagram. If that confuses you, then just ignore that for now. Think of the idea of the electrons moving closer to one atom. So the shared pair, as said, is displaced towards the atom with a higher electronegativity. This results in a polar bond. That's what we mean by a polar bond. It's a covalent bond where the electrons that form the covalent bond are closer to one atom than the other. If it's just a normal covalent bond, a pure covalent bond, then those bonded pair of electrons, they're right in the middle between the two atoms. There's no difference in electronegativity between the two atoms, therefore these two electrons remain in the middle. This is what I mean with the electron cloud. You can see very clearly that because chlorine, you know from the trends of electronegativity, it will have a higher electronegativity than hydrogen. We have a distortion of the electron cloud. It is greater on the side of chlorine. The two electrons that form the covalent bond between hydrogen and chlorine, they're more attracted to the right-hand side, so to here. That means we're more likely to find electrons on this side. There are more of them spinning around and moving here. Yes? This is why we use these symbols as well, delta plus on the hydrogen side and delta minus on the chlorine side. The atom with the higher electronegativity will have the minus, and the atom with the lower electronegativity will have a plus. That's always the rule. Now this arrow here just means the dipole. The dipole is the separation of the opposite charges. So if you think about it, we have a pole being formed on this molecule here. One side is positive, one side is negative, just like we have poles on a magnet. One is north, one is south. They oppose each other. Well, plus opposes negative. So even though this is a slight charge, it's not full, remember. That's why we use delta. It's still a difference in charges. They're still separated. That's why we have a pole. And a dipole is this separation of them. And this arrow just shows this dipole. The arrowhead itself will be pointing towards the negative side, and then the line, this vertical line, will be on the positive side, okay? So that's the idea of a polar bond. However, molecules very often have more than two atoms. That means that they'll have more than one bond, and these bonds can be polar. So therefore we can also decide whether the molecule overall as a whole will be polar or not. That means that also on one side of the molecule, we will have an accumulation of negative charge, delta negative, and on the other side of the molecule, on the opposite pole, on the opposite end, we will have an accumulation of positive charge where there are fewer electrons. That will be delta plus. Now you're probably thinking now, well, if polar bonds are present, then surely the whole molecule will be polar. No, actually. It turns out that we need to look at the geometry, the shape of the molecule. That will decide whether the molecule is polar or not. And this is where all our VSEPR theory and shapes of molecules comes in very handy. It's to do with the idea of symmetry. If the geometry of the molecule is symmetrical, then the dipoles, remember those are just a separation in opposite charges, they will cancel each other out. And so the whole molecule will be non-polar. What does it mean to cancel out? Well, think about this idea of tug of war, when we have two sides pulling a rope away from each other. If they're both pulling the rope at the same force, at the same rate even, then nothing's going to happen. We have no overall, no resultant force. We can kind of link this to physics. We don't have a resultant force because the forces are equal and opposite. They're acting in opposite directions and they have the same magnitude. That means that we will have no overall movement, no resultant force. It's very similar here. If the dipoles are acting in opposite directions, and they will do if the molecule is symmetrical, that means that whatever force these dipoles are exerting, it doesn't matter, they cancel each other out. So let's have a look at ammonia again. This is our geometry of the molecule. So first of all, remember, nitrogen and hydrogen have different electronegativities. That means that our bond NH is polar. However, at the moment, this does not tell us that the whole molecule is polar. We don't know yet. We now need to consider the geometry of it. By the way, what is the name of this shape? Yes, it's trigonal pyramidal, and trigonal pyramidal is not symmetrical. That means that the dipoles do not cancel each other out. Yes, we will have overall poles. Yes, we will have an accumulation of negative charge on one end of this molecule. That means that the whole of ammonia, overall, it is indeed polar. Let's have a look at this more closely just to illustrate the whole idea. So here is our dot and cross diagram of ammonia again. Remember that nitrogen is more electronegative than hydrogen, so all these bonded pairs, they move towards nitrogen. Nitrogen attracts them. Remember, because of all of its properties that we talked about. So now let's consider the trigonal pyramidal geometry, which would look like this. We can see now, therefore, that on this top end here, where nitrogen is, we have an accumulation of this negative charge. All the electrons, they're all gathered there. At the bottom, we have no electrons. We have a positive charge then. Remember, it's still only slight, and only slight at the top. So therefore, because nitrogen is more electronegative and the hydrogens are less electronegative, this end of the molecule here is delta negative, and then all the hydrogens are delta positive. They're all bound towards the nitrogen. We have an uneven distribution. They're all displaced towards this top end. That's where our one pole is, and then we have other poles around the hydrogens. That's why the whole molecule of ammonia is polar. Now there's one other important factor to consider. If a molecule contains different ligands, so remember those are the atoms that are attached to the central atom, if they're different, that means that the bonds between the central atom and the ligands, if they're polar, they will differ between each other Because remember, if we have different atoms, atoms all have different electronegativities, well therefore we will have different polar bonds. The polar bonds will have different strengths, and the correct word for this would actually be dipole moment. So the dipole moments would be different. So in a molecule, if we have both polar and non-polar bonds, or in a molecule we have only polar bonds but they are all different, their dipoles are different because all the atoms surrounding the central atom are different, then automatically the molecule is polar. We don't need to look at the geometry at all. Already, because we have different dipoles, we will already have an overall dipole moment. We will already have an uneven distribution of electrons just because the forces, these moments of the dipoles, are different. That means we will have an overall polar molecule. So we don't need to go ahead with looking at the geometry. If we do need to look at the geometry, however, we need to find out, obviously, whether it's symmetrical or not. And you're probably asking the question, well, how do we determine whether it's symmetrical or not? In maths, yes, that very often is quite easy. This time, though, it isn't. And in the exam, yes, you can maybe try to determine it yourself. However, there will be many unexpected surprises, shall I say. So let me show you which shapes are symmetrical and which aren't. So here are all the ones which are symmetrical, so therefore the polarity will be non-polar overall, provided that all these ligands here, all these blue circles here which represent these atoms attached to the central one, are the same. If they're different, then ignore all of this, molecule is polar. So first situation here at the top, we have one central atom and two situated either side. So let's have a look at carbon dioxide a bit closer. Carbon and oxygen have different electronegativities. We have a different electronegativity. What do we have therefore? Yes, we have a polar bond. So we have one polar bond between carbon and oxygen here and one here. But because oxygen is more electronegative than carbon, the electrons move towards the oxygen, so the dipole orientates towards the oxygen. This means that the dipoles are acting in opposite directions, and because this geometry is symmetrical, the dipoles cancel each other out. So just remember this tug of war. Remember, think of the oxygens pulling this rope, and they're both pulling it at the same rate, at the same force, because they both have the same electronegativities. It's the same atom. So overall, we have no polarity because the dipoles cancel. Same idea with trigonal planar. This time it's just a three-way tug of war. We can also have a four-way tug of war with tetrahedral, and 5 with trigonal bipyramidal, and even 6 with octahedral. All of these geometries here will be symmetrical. And as I did say, you might have thought that, well, AX4, AX5, they don't seem to be symmetrical, and they don't indeed in 2D. But remember, we have to consider everything in space, stereometrically, so in 3D we do have symmetry. Right, and therefore these molecules here will be non-symmetrical, and therefore they will provide a polarity. The molecule will be polar overall, but that's only if polar bonds are present. That's only if we have atoms of different electronegativities. If not, no polar bonds, molecule is non-polar. So first example here, and to be honest really I should have drawn these two circles in different colours, but oh well. Hydrogen and chlorine, they're two different atoms, different electronegativities. We have an overall dipole moment, therefore hydrochloric acid is polar. And then the rest are pretty much the ones that have lone pairs. Remember that lone pairs, they reduce the bond angle, so therefore we're going to have a non-symmetrical shape. The ligands, they will be pushed away from the lone pairs. So in 3D even, we're not going to have symmetry. That means that there is no way that the dipoles can cancel, so the molecule will be polar overall. So let's now go through the thought process of deciding whether a molecule is polar or not. First question you ask yourself, are polar bonds present in the molecule? The answer obviously is either yes or no. Actually, to be honest, before you even ask this question to yourself, you should think, right, okay, is this molecule ionic, covalent, or metallic, or whatever? If it's ionic or metallic, so if it's charged, that's it. We're not talking about polarity. We only talk about polarity with covalent molecules, okay? Remember that. So yes, our answer is either yes or no. If it's no, what is the conclusion? Very simply, molecule is non-polar, no polar bonds. If there are, then we need to ask ourselves the next question. Is the geometry symmetrical? If no, then that means the dipoles do not cancel out, the molecule is polar. If yes, then the next question that we need to ask is, right, Do all the dipoles have the same moment, i.e. are the forces the same? Are the atoms that surround the central atom the same? If they are all the same, if they are not the same, that means we have different electronegativities, that means we have different strengths of the polar bonds, that means we'll have an overall dipole moment, and therefore the molecule is indeed polar. If they're all the same, if the geometry is symmetrical, great, molecule is non-polar. So I strongly recommend that you learn how to go through this process of elimination, really, to decide whether the molecule is polar or not. But when answering exam questions, we don't draw this diagram, we would rather state in a logical order all these points. Start off by saying whether or not there is a difference in electronegativity between the atoms, and how significant this difference is. By that I mean that if the difference is very small, or virtually zero, then it's just a pure covalent bond, isn't it? If it's greater than 1.8, then it's ionic. Now, of course, as I said, you don't need to know the values, but you can include this statement as well so that you can then support your answer further on. And hence we can state whether or not there are polar bonds. Then we need to talk about the geometry of the molecule. And if the question asks, why is this the specific shape of this molecule, then we talk about VSEPR theory. So basically you need to go through the whole idea of electron pairs repelling each other, lone pairs and all of that. You say that, and then whether this shape is symmetrical or not, hence whether dipoles cancel or not. And finally, then you're able to give your verdict, i.e. the conclusion, whether or not the molecule is polar. Now, of course, if there are no polar bonds, then all of these 4 points here we can ignore, and you just go straight to your conclusion. Finally, for today, let's just go over a few examples that will illustrate the points I was trying to make earlier on. First of all, let's have a look at boron tetrafluoride. Here it is, BF3. It's a trigonal planar geometry. All the ligands are the same, they're all fluorines, all the polar bonds are the same, and because the geometry is symmetrical, it is non-polar overall. Nice and simple. Let's now take another molecule which is trigonal planar, COCl2. As you can see, we have different ligands. Oxygen has a different electronegativity from chlorine. That means that the CCl bond is different from the CO bond. We have different dipole moments. That means, regardless of the geometry, we will have a polar molecule, okay? Next example, ethane. Now this is where it gets quite hard, and you do actually have to apply your knowledge of shapes of molecules. This is a very common application question, where we kind of have two parts to the molecule, where one area will have one geometry and then another area will have either the same one or a different one. Same principle still applies. You do the dot and cross diagrams for each part or each half, whatever, of the molecule. Then you look at the central atoms and you decide upon the bonding between those two. So this is what I mean. This is the geometry of ethane. So on the left we have one ethyl group, on the right we have the same ethyl group, and they have their own specific geometries. You just need to draw them separately in the dot and cross diagram to determine what shape it would be, and then you just join the two central carbon atoms with a single bond. Well, we know that that's a single bond from our organic chemistry knowledge, even from GCSE. Now keep in mind that CH is a non-polar bond, as we saw. It's an exception, so the difference is quite small, so yes, it does make sense for it to be non-polar, and that's it. No polar bonds, geometry doesn't matter, non-polar molecule. Now if we have a look at ethanol, C2H5OH, it is a very similar geometry, but this time one of the hydrogen atoms is replaced with our hydroxyl group. This time C and O, they have a significant enough difference in electronegativity for it to be a polar bond. Also, the COH, this area here, it will have an angular geometry. This means that it's not symmetrical. Overall, therefore, the molecule is polar. And I have a feeling that the exams can be even harsher, and they will ask you to determine whether or not molecules such as sulfuric acid are polar or not. Same rules still apply, just remember that you have to treat each part of the molecule separately, determine the molecule for each area, and then join it all together. See if there are any polar bonds first of all, and secondly, using the geometry, determine whether or not the dipoles will cancel. That is it for this topic. As you can see, it's a very long video because it is very important. I strongly recommend that you re-watch this as many times as you need so that you're happy with everything, and then go away and practice many exam questions. There are loads of them online. You can find them anywhere. It's very easy. If you then have any questions regarding them or this topic in general, please ask in the comments. I will definitely answer. Thank you very much for your attention. Thank you very much for liking and subscribing. See you next time. Goodbye.